Okay, the concept of curvature is actually a fairly simple concept. You have your unit vector in your direction of motion, wherever your direction of motion is, and the rate at which that changes with respect to distance along the curve is called your curvature. Now, to get the rate of change of t, when t is given as a function of time instead of distance along the curve, it's how fast t is changing. Okay, imagine you're driving along a curve, you're speeding up, slowing down. You look at how much your direction changes and divide that by how fast you're moving. Okay, because the faster you're moving, the faster your direction changes for a given curvature. If you divide how fast you're moving into the rate at which your direction is changing, then that corrects for the fact that maybe you're moving faster or maybe you're moving slower. So curvature is how fast t is changing, corrected for how fast you're moving, and that means you're dividing the rate of change of the unit tangent vector, the derivative of the unit tangent vector, by your speed. Okay? And it's the magnitude of the rate of change of your unit tangent vector. It doesn't matter what direction you're changing. You'd have the same curvature going off this way as going off this way. That's the idea. So we have this definition, this K thing, or kappa, using the Greek letter corresponding to K. It's the magnitude of t prime divided by the magnitude of v. But of course, the text probably writes this as magnitude of t prime divided by the magnitude of r prime. Are there other formulas for curvature? And we might be able to talk about those, but let's get the basic one down here. Now, I started out doing the derivative of t, where t is up here, and tried to break it down and tried to keep it on the board, and it wasn't going to happen. So we're going to forget about calculating that derivative for right now. I do want to go on and talk about what happens. You've got this curve here, okay? This curve in space corresponds to the path of the r of t vector. And that curve is nicely defined by the, that is the r of t curve. So here's your r of t. For 0 less than or equal to t less than or equal to 10. This curve lies above this straight line. So it's like you can make a picture of it, and if you straighten out that picture, it looks something like this. Maybe it's just an arc of a parabola, maybe it's a part of a circle, but maybe it's not symmetric. We can analyze all that. I can tell you in terms of this that it, whether it is symmetric or not, because, well, I'm not going to go into that. We didn't go into that in class. The point, though, is that what we want to do now is we want to take 3 points along this straight line, the projection of the r vector into the xy plane that you get just by leaving off the k component. Okay, we want to take 3 points along this line and then the corresponding points on the curve, which are easy to calculate. If I gave you the t value here, here, and here, you plug it in to r of t and you get the k component, the z value for the point, as well as the x and y values. If I do that for 3 points, it might look something like this. If we look at it from this angle, so we're looking straight on it. Okay, we've got the point down here. Need the orange chalk. Point here, point here, point here. That's these 3 points. Then we've got this point and this point and this point, these 3 points. There's a vector from each point to the next. There's a unit vector, the green vector from each point to the next. The purple vector, of course, is the vector from each point to the next. There's a difference in these vectors. Okay, now, they don't quite have the same direction, although if these points are really close by, you would have to carry out calculations to a number of decimal places to make sure you see the difference between this vector and this vector. If you take the difference between these 2 purple vectors, could be indicated here, okay, then you've got, this vector and then this vector. It's a little different angle, and you've got the difference of those vectors. Well, that's a vector here, and that vector is going to be approximately normal to your curve, and one thing you'll be asked to do for homework is to verify that.